Hi, my name is Robin Hesse, and I'm happy to present our paper, FunnyBirds, a synthetic vision dataset for part-based analysis of explainable AI methods, that is joint work with Simone Schaub-Meyer and Stefan Roth from the Technical University of Darmstadt. I hope you enjoy. Given an input image, a deep neural network, and the corresponding output prediction, one of the major questions in XAI is, why does the DNN predict that output? Over the time, various approaches, such as attribution maps, binary importance maps, or prototype explanations, have emerged that aim to answer this question. However, evaluating these explanations is a largely unsolved challenge and a motivating question for our work. The reason for that is due to what I like to call the funny bird and egg problem of evaluating XAI methods. On the one hand, we need XAI methods to know how deep models are working. On the other hand, we need to know how deep models are working to evaluate XAI methods. This leaves us stuck in a loop because there are just no crown-tooth explanations that we can compare to. To still evaluate explanations, the community came up with proxy tasks where crown-tooth explanations are approximated. One of the most popular approaches are feature deletion protocols where we, for example, incrementally remove individual pixels or patches in the descending order of their estimated importance to measure the effect on the model output. If we have a good explanation, meaning that the attribution map faithfully indicates the most important pixels, they will be deleted first, leading to a fast output drop and a small area under the output curve. However, these approaches usually come with several limitations, such that they work only on a semantically less meaningful pixel level, that they introduce out-of-domain issues because the training set contained no images with deleted pixels, that they exclusively work for attribution maps, and that they only evaluate a single dimension of explanation quality. These four limitations will guide the design of our approach, that is a combination of a novel dataset and accompanying evaluation protocols. Our dataset is built around concepts or bird parts that we manually design. For example, we have different eyes, beaks, and wings. Using unique combinations of these parts, we instantiate 50 different bird species that we call funny birds by adding the parts to a neutral body and then adding clutter and changing the viewpoint to make the image more challenging. The most important desideratum behind our dataset is that we have full control over and knowledge of our scenes. Having full control over each scene allows us to perform image space interventions that we can use to generate ground-truth explanations for the model under inspection, to which we can compare our estimated explanations. For example, we can remove the feet of our bird and observe that the output score drops only marginally to 0.8. When instead deleting the beak, we observe a much stronger drop to 0.4, which indicates that, under some assumptions, the beak is significantly more important than the feet. This idea of performing image space interventions to estimate ground-truth explanations can be extended to multiple protocols that you can find in our paper. As the interventions are now on a semantically meaningful concept level, we can tick off the pixel level issue, and by including images with deleted parts in a training set, we can also add a checkmark to the out-of-domain problem. The next challenge is to include multiple explanation types, such as attribution maps or prototype explanations, in the same framework. To do so, we define more general tasks, so-called interface functions, that indicate if a part can be considered as important and how important that part is. For example, in this attribution map and prototype explanation, we can consider the tail to be important because it contains high attribution values, respectively a highlighted patch. Building our framework around part importances allows us to abstract away the specific explanation types, and we can also tick off the limitation of only including attribution maps. Our full evaluation framework consists of 5 different dimensions, including, for example, the standard classification accuracy and correctness that closely follows the presented idea of deleting individual parts and measuring the rank correlation between the ground-truth importances and the estimated part importances. The number in the middle is the average of the explanation quality dimensions completeness, correctness, and contrastivity. Now that we understand the high-level idea of our work, let us have a look at some of our results. First, the best performing method in our framework is BACnet, which could be due to its internal model structure that is nicely aligned with the explanatory power of an attribution map, because individual patches are processed more independently. Second, evaluation scores for the same XAI method are consistently better on VGG16 than on ResNet 50, indicating that different backbones vary in their explainability. Third, the ranking of input times gradient and rise changes across different backbones, showing the importance of evaluating future XAI methods on multiple backbones. Please refer to section 5 of our paper for more results and additional custom evaluations that go beyond the presented framework. Thank you very much for following our talk. We hope that you have enjoyed it.